So we're continuing with the non-dimensional interaction diagram. We just finished it last time, and we talked about how to calculate the gamma value. Today we're going to go over the design of short columns with a few hints that we have here. It says for eccentricity ratio, E over H, that are less than 0.1, and we don't have to do that check, but we know that for such a small eccentricity, it means that we have such a small moment on the column. We say a spiral column is more efficient in terms of load capacity, but remember that spiral columns are only applicable for rounded or circular columns. For eccentricity, as they go higher, a tight column would be more efficient, and especially it is more efficient because in the direction of the moment, your distance between your two lines of reinforcement will be very effective in resisting your moment. So remember this fact. What we're talking about here is the bigger the distance you have between your steel reinforcements on the two sides in the direction of the moment, the better capacity you will have to resist this moment. And then tight columns with bars on four faces are used for ratios less than 0.2, and also when moments exist about both axes. If we have such a configuration of moments, you have M1 and M2 in columns that are subjected in the 3D to different loadings, then you would better put these reinforcement on all faces, because you know that every face, every two two opposite side reinforcements will be resisting a moment in a certain direction. Now, reinforcement limit, this is the part of the code that talks about it. It is between 1% and 8%, as we agreed last time. Minimum reinforcement, there is some verbatim here that we have in the old code that talks about the reinforcement ratios and how they evolved. It's good for your read to understand how the code evolved to what we have now. And this is the maximum reinforcement. Now, the design of short columns, choice of material properties, and reinforcement ratio rho. We said in the small buildings, the concrete strength is selected to be equal to that of the floors, which is very common that for small buildings you specify F prime C in columns to be the same as F prime C in the floor itself. Why? Because you have such a small load that will not matter much in your size of the column. But when you go to tall buildings, you start seeing in the notes of your drawings that you have a strength, F prime C, for columns that are higher than those for floors. And the reason for this is because as your building goes taller, you would want to make your columns smaller. And the reason for this is because you want to utilize your spaces in your rooms. So the bigger the column becomes, the worse it is for the space utilization inside your rooms. The vast majority of columns are built with a steel yield strength 420. I guess in the Middle East, and a lot of times you might not find the 420. Then you go with the 360 and make up for the difference. Although the ACI allows up to 8%, it is very rare that we see reinforcement ratios that are higher than 3%. Simply because this is becoming, or this will become uneconomic, and you will not see it as a practical number. However, when it comes to such buildings, structures like bridges and very highly loaded tunnels, you might go with high percents in steel in reinforced columns. So the economic tight columns will be within the 1 to 2% for the steel reinforcement ratio. Even number of bars are used in rectangular and square columns, right? Because you will have to satisfy all faces with those numbers. Now, how do we start as an estimate for the column size? If we place everything on one side in the equation that we had before, which is the phi PN equation, so we substitute phi PN with PU. And then we put everything else on the other side, get all the factors outside, and then put area gross on one side. Now, if I substitute this with a 0.01, which is 1%, I can simply find what's the proper area gross. Now, this will be based on the assumption that I don't have any moments. Again, where did this come from? Very simple equation of Ppn becoming Pu equals to 0.8 times phi times 0.85 F prime C area concrete plus F yield area steel. Very simple. So I substituted area steel with area steel over area gross, and I got area gross outside with this here being with the rho of 1%. Now, you will tell me, what if I have moment? I would say that the better option if you have a moment is to start with a lower rho. Now, in this case, this will be bumped up to become a higher rho to satisfy your moment requirements. We'll see this down in our values. Now, the difference between those being spiral, and now this becomes 0.85 phi, right? And the phi here for a tide is 0.65, while the phi here for the spiral is 0.75. In this case, the difference would be the 0.5. Now, those equations, you don't have to follow them. The only thing they will do for you is they will save your time in selecting your column size, okay? Now, spacing and construction requirements for ties. Now, what are ties? Those ties are the ones that confine our columns, our column reinforcement together. Is there any requirement for this distance? Or is there any requirements for the ties themselves within the section? Now, to know what ties are doing, they're mainly for 4 reasons. To restrain the longitudinal bar from buckling out. So I don't want this to happen. I don't want the bar to buckle out. So I pull it down with those ties. They hold the reinforcement cage together during construction. Now, which makes life easier. So you will just finish all your cage as one set of reinforcement and you transfer it to your column. They properly detailed columns or ties, they confine the concrete core and provide increased ductility. Remember, as we said before, that tie will put so much pressure as the column is loaded on the core concrete, which is the concrete that is inside your cage. Now, there is core concrete that's inside the cage, and there is cover concrete, which is outside. Now, the cover normally is not really under much of work when it comes to lateral loading. So what these ties will do is they will apply the compression back, the compression that comes from the top, they will apply it back to the core concrete, and this will maximize your ductility, which is the ability to keep the failure very delayed up to a higher loading or higher displacement. And then the last thing is for the ties, they work as shear reinforcement. If you have side load like this, lateral loading, where are your stirrups? Now in this case, if I consider this like a beam, which would crack like this, my ties in the columns are considered my stirrups that will work for shear or as shear reinforcement. The requirements for the ties are, now I have this as my longitudinal and those as my ties, right? And those here as my ties. The first requirement is, which phi do we use here? So they said, look at this phi first, longitudinal bars first. If they are less than or equal phi 32, then use, for those guys, phi 10. If they are more than phi 32, then use phi 13. Simple. So the bigger longitudinal bars will require a bigger tie. But it's very simple. It's only 2 sizes that we're looking at. Phi 10 and phi 13. Number 10 and number 13, of course, metric we're talking about this. Now, the second requirement is the spacing between the bars. Now, that every tie to the next tie, center to center. What is the spacing? They say it's the least of those three. What are those three? 16 the bar diameter. Which bar diameter? This guy. So this guy has a diameter dB. 16 times this. Or 48 times this. So this one is dt. So 48 times this. Now you're looking as always 16 might be bigger. If you have a really big dB, 16 times a bigger bar could be bigger than 48 times the smaller bar. And then the last requirement is, you look at the column itself, right? Those are my bars. Now, the least of the column size sides. Okay? So this one is x. So we compare this number to this number to this number, and we take the least of them as my tie spacing. Of course, we round them down to a nice number and keep going. Simple. So the dB is the longitudinal bar, and the dt is the tie diameter. Now, the typical arrangement of ties in such rectangular columns goes like this. We usually have the very big one. This is the outside tie that will take all of them. And then we start putting these rectilinear or smaller ties to tie down more rebars. And the way we do this is we look at the spacing between the bars. We have to calculate that spacing. If the spacing is more than 150, then we must tie every bar. If the spacing is less than 150, then we must tie every other bar. So there is no chance we will have two consecutive bars that are not tied. Again, I should not see such a shape. Do you see this shape here? Now, think about this. If I'm starting to put those bars, here is one. Here is another one. Right? I'm missing something. Regardless of the distances, once I see this shape, I will say, since you have two consecutive bars that are not being held by rectilinear ties, there's something wrong. So I must have another one here, at least. Okay? And then how about those? Oh, I start saying, okay, now I need to start looking at the distance. What's the distance here? Is it 150 or less? Then you're good. If it's more than 150, then I have to hold it. So this is how things work. Taking an example now, example 10.2, if we use an f prime c equals 28, f yield equals 420, for a 400 by 400 column, so this here is 400 by 400. But we can obviously see that the reinforcement is only on two sides, which means we will have some moment somewhere on this direction, right? And that moment will be resisted by those two-side reinforcements. Now, use the interaction diagrams to compute the maximum MU that can be supported if the column is subjected to a PU equals 1,000. And then the second question is the maximum PU if the column already has an MU equals 150 kilonewton meter, and the maximum MU and PU for an eccentricity equals 100. Now, this is not very practical. What's more practical is 1 and 2. To know how much moment I can put at a certain load, and to know how much load I can put at a certain moment. Looking at the configuration of the column, I can simply calculate my gamma. How do I calculate the gamma? It is the distance between center to center, this distance, divided by the whole distance. Right? So I have those two distances divided by each other, have 400 minus the two covers, minus the two stirrups or ties, minus half a bar and half a bar, that's a 1 bar, divided by 400, that gave 0.69. In this case, I can use the curve of 0.7. It's pretty close, right? And now what's my rho? If I have 8 number 25, I just calculate the area divided by the area gross. That gives me the rho equals around 2.5%. Clear? Now I can select the interaction diagram that looks like this, because this is how my column looks like. It must contain my gamma equals 0.7. And now what do I know? I know rho equals 2.55%. Then which curve of these curves will apply? I have the curves telling you the 1%, the 2%, the 3%, 4%, until you go all the way to 8%. Then I will have to take an imaginary line, and that imaginary line is about where the 2.5% is, and run it between the 2 and the 3%. So this would be the 2.55%. Now this line here is for rho equals 0.0255. Okay? This is the rho I just obtained up there. Now, my two values that I'm looking for is the Kn and the Rn. Very simple. I have the first and second equation. One of them contains mu and asking for the pu. The other one contains the pu asking for the mu. So in this case, knowing the pu, I can calculate the Kn by dividing by phi f prime c area gross. I got 0.343. I go this way until I hit the curve. I go this way until I hit my curve, which is this curve, and then I go down. I got a value here. What is this value? It's the Rn. So now I got from the graph 0.23. I calculate, I plug it in here and solve for mu. This whole thing is mu. Okay? Now I find mu equals 267.9. So if I applied a 1000 kilonewton axial, I can maximum apply a moment equals to 267. I cannot put any more moment than this. Any more moment will get me this way, and it will be unsafe. Now let's go to the second question. Knowing the mu equals 150, I can calculate Rn, and then for the same curve, which is the curve equals to 2.5%, I will go up with this curve, with this value, hit my curve, and then go to the side to calculate my Kn. Calculated my Kn equals to 0.86. From the Kn, go back to this equation and find Pu. That will be equal to 2,504 kilonewton. If I go any more than this, it will drive me up and it will be unsafe. Now the last question is, I know E. E equals what? 100 millimeters. While the side equals 400. So I know E over H equals 0.25. Where is the 0.25 here? Where is E over H? It's these values. So I would know that my E over H equals 0.25 to be this line. You see this line here? And then draw the line where it should be. And then I know my curve. So where this line intersects with my curve, which is my rho curve, it gives me a point, which is this point. From this point, I go down and I go to the left. I'll find Kn and Rn. By knowing Kn and Rn, I can calculate mu, and I can calculate pu. So for the given E, I know E over H, I was able to find Kn, Rn, and then I calculated Pu and Mu. Now, here's a kind of a summary of what we do. In the design of short columns, we assume a reinforcement ratio to be between 1 and 3%. Select the trial cross-section B and H, and we said that there is this equation of area gross that we can use for the trial. Area gross trial could work for us. Calculate the ratio gamma. Calculate Kn, Rn, where the area gross is the full section area. From the design charts, read the required reinforcement ratio, get back and read your ratio, and see if it is within the number that you selected. If yes, then select the area steel to be rho times BH. Use table A2 to select the reinforcing bars, design your ties, and draw your cross-sectional area. Very simple, summarized design steps. Here's the area of steel bars from table A2. Let's take another example. Design a short tied column with a square cross-section to support a PU equals 1550 and MU equals 150. Now I know both of them. I know PU and I know MU. The reinforcement will be distributed on all faces. So I know that the column will look like something like this. Now I know which types of interaction diagrams to go after. And it tells you that the F prime C equals 28 and the F yield equals 420. And to start with longitudinal bar size equals 29. So this also saves us the time to try thinking about the gamma, because gamma will require that you know the bar size. So we assume that it's 29 and we go with this. Now, the first thing is, I don't know my reinforcement ratio. Reinforcement ratio equals what? We don't know. So we will start with something. We will assume that it is 1.5%. It's a good assumption. Now, 1.5% will be plugged in the trial equation for area gross. I calculate area gross to be 112,974 millimeters square. If I assume that it's a square column, I very simply take the square root of this area. I find the cross-sectional area to be 336. I can round it up to be 350 by 350. Now, what if I was told that this column is not square? It's rectangular with a certain size of one of those. Then I just design my section to be whatever size was given to me. I play with one side and fix the other side, depending on the givens. Next is to calculate my gamma of the section. Now I know that H equals 350. I just minus the two covers and minus the two diameters, which would be phi 10. Why phi 10? Because this is less than phi 32. And then minus half a bar and half a bar, that's a full bar, 28.7, divided by H, that's equal to 0.64. Now, in the interaction diagrams, I have a 0.6 interaction diagram and a 0.7 interaction diagram. So what do I do in this case? I will have to work my way through the 0.6 and the 0.7 and do all the necessary work for the 0.6 and the 0.7 and then interpolate between them. Okay? Because I don't have something close to the 0.64. So I calculate my Kn and my Rn. Very simple calculation. I got 0.7 and 0.19. I'll check the graphs, make sure that the points are in the compression zone to ensure that phi equals 0.65. So I'm going to the interaction diagram of 0.6, and I'm going to the interaction diagram of 0.7. Both of them. What are the required to be done? I plug in my Kn and Rn. I go inside and I find a point. Now what am I getting out of this point? I'm getting the location of my steel reinforcement. So now this here will be what I'm looking for. I'm looking for this row. So as I read off this, I have this curve between 0.04 and 0.05. Leaning a little bit more towards the 0.05. So maybe in the upper 0.04. My next curve, I go down here. I will find that it goes to around 0.3, right? A little bit less than 3%. A little bit less than 0.03. And then I go next to getting those. I guess this is a typo mistake. This should be 0.029, not 39. It's actually 0.03. Okay? And then I interpolate between them. I find my row. I plug in my row and get my area steel, find the number of bars needed, and then distribute them. Okay? Very simple steps. I go them. Now, my unknown in this was area gross and row. Okay? So now we were able to find area gross and row. I go here to, since the longitudinal bars are number 29, number 10 ties will be used, and then in this case, the distance between them is going to be between the 16 dB or 48 dt, or the smaller size, which is 350, which controlled. So we choose the spacing between the bars to be 350 millimeters. Now the summarized design, I have 8 bars, number 29. Distance between the ties is 350. Number 10 ties. The column size is here. And I need to check what the spacing. Now the decision, do I need to put such a tie or not? How do I decide on this? I will have to calculate the clear distance between those 2 bars or those 2 bars. Okay? So now what I'm going to go with is to calculate this distance. This distance is 350 minus the 2 covers, minus the 2 ties, minus 3 bars, 1 bar, 2, and 3, and then divided by 2, because here is 1 and here is 1. That gave me 82.5. If it's less than 150, now I will hold every other bar. I have 1 bar being held here, 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 and here. I only have those left. Then I am good, and I don't need to put internal ties inside this column. So there is no need for extra ties.